universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Well, hello there, everybody. This is Mark D'Antonio, and down there is Tara. Over there is Daryl Mason, and over here is Amanda. How are all of you guys doing tonight?
Feeling like a Brady.
Doing good. You're looking like a Brady.
Yeah.
Yes, welcome to SkyTour Radio, folks. And I just wanted to let you know we got a special show for you tonight. I try to think that we always have a special show for you. Before we get started, I just want to let you know that, we would like to have you subscribe to the companion stream for SkyTour Radio, and it's called SkyTour Livestream. It's live deep sky astronomy on clear nights, and you get to see these amazingly gorgeous imagery from all over the universe. We just pull this stuff in for you. And the thing that we do is we use our wonderful telescopes. We have telescopes now in Arizona, in the desert, and here in Connecticut, continuing the tradition of SkyTour Livestream East with SkyTour Livestream West. And we bring you the night sky. We see glittering jewel boxes of rich clusters of stars, wondrous phenomena in the universe like stellar nurseries, and like those are places where life may eventually, seed and take hold. So, and we also see these once-in-a-lifetime interlopers, like comets that come zipping through our solar system and then leave forever. We also see periodic ones that come by, like Comet Neowise and Comet Holmes and others. And we show them all to you live in our telescopes. And it's also a stream, as Amanda and Daryl, who are also on that stream, will tell you. It's a stream where you guys can be in charge if you want to be. You can tell us objects you'd like to see. And if they're available, we'll show them to you. Our very active chat group asks questions that we will answer to the best of our ability. And you guys are the most knowledgeable audience on Earth, those that follow SkyTour Radio. And we are really, really impressed with you. We all are. In addition to SkyTour Livestream, you might want to consider the shameless plug here for this book called The Populated Universe. It's a book about life in the universe and how life in the universe may very well be the rule and not the exception. It's just a little something that I came up with. It only took a few years to write, but it was really quite a wonderful journey doing this writing, because I am an exoplanet guy. You know that I'm an astronomer, but I believe that there's life everywhere we look. And I think we're going to find it. And guess what? Maybe we'll find it on Mars with this Perseverance mission. It's possible. There's a lot. Yeah, right. I mean, there's a lot yet to see, But SkyTour Radio is here for all of you, and we also have a call-in line. I don't even know the status of the call-in line, Amanda. I don't know if you know.
We will have to talk to our wonderful producer Bill about that. It can be done. I don't know if he wants to go through all that, but
that's okay.
Possibility for the future.
Okay, very good. And of course, tonight we're also going to have another feature that is going to feature Daryl Mason, and we have a nice new interactive planetarium that Daryl's going to bring up and be able to show you the wonders of the coming sky.
Ta-da!
Ta-da! That's right.
Ta-da!
And if it messes up, we'll say things like, wow, it sure would be nice to have some grenades there, Mel, or something like that, which is Daryl's favorite line. In any case, if you have an email or a message you want to send to us, you could reach us at skytourradio@kgraradio.com. And I think that's even still valid. A lot of things have been in flux with KGRA. A lot of things changed, but I think that domain is still active. And that's another question to you, Amanda. I don't know if it is. That's something you have to tell me. You're right over there. She's right next to me, right there. So I bang the box. Boom, 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 boom. Amanda.
Sorry, tell me again, what are we looking for?
Is our email still active? Skytour.
It should be. Yeah, I don't see why it wouldn't be. We if all goes well, we should have our phone lines up and running for the show next week. If you guys want it. You guys in chat, let us know. Do you want to talk to us? I don't blame you if you don't. But if you do, well, I mean, they might want to talk to Tara.
That's
get
correct.
to know Tara a little better. So yeah, we'll get those lines out for you next week.
Yep, very good. I think that's awesome. Now, first up, I have to acquaint you guys with something that has to do with our periods of time, our historical time frames here on the Earth. Why would I go through that boring stuff? Well, because it really is important for the story that I have to bring you tonight. You see, you hear about eons, you hear about eras and periods and epochs, EPOCHS, epochs. And we discuss these all with Earth history, the Permian period, the Jurassic period, things like that. And what do they really mean? Okay, and what are those time periods and what do they actually refer to? That's something that's really important to talk about now, to show you why right now. Here they are. Okay, the eon is the longest span of time. It's about 1 billion years. Okay, and each eon can be composed of several eras, which last several 100 million years. And then within those eras, you have periods. The Quaternary, Neogene, Paleogene, and then that's the Cenozoic era. And in the Mesozoic era, we had the Cretaceous, Jurassic, Triassic, Permian is in the Paleozoic, and thus it goes on and on. Well, what's interesting is the one over here on the right that you can see just below on the epoch column over there, it says Pliocene, not Pleistocene, but Pliocene. Interesting thing about the Pliocene, something happened there that we hadn't seen before. It's another extinction event. So the Earth, as I have said in the past, has suffered 5 major extinction events, whether through its own failures of biological diversity or through its own or through an external impact or something. But there's actually now 6. And it happened in the Pliocene. All right. What happened? It was 2.5 million years ago in the Pliocene. And this event actually had implications for life all over the planet. And it also has off-world implications. That's right, off-world implications. What does that mean? Well, stay tuned, I'll tell you. It means that at the time we had very large animals, and we call large life animals megafauna. Okay, fauna, life animals, and then megafauna, huge animals. Well, yes, dinosaurs were very large animals as well. But at this point, dinosaurs no longer existed. Right? This was a time that was only 2.5 million years ago. The last big dinosaurs were 66 million years ago. So this particular place in the Pliocene, which lasted from 5.3 to 2.58 million years ago, it ended. The Pliocene ended because all of a sudden, out of nowhere, and I don't know why it hasn't been seen before, most of the megafauna on the planet died off. For instance, that was the time when the Megalodon shark, a 50-foot-long shark, existed. The Megalodon was this massive, massive shark, and it was actually so big that you could actually stand up in its jaws. It was that big.
I saw that movie.
Yeah,
I saw it too. Yep.
Pretty cheesy movie.
Oh, maybe so. Maybe so.
So big though.
Well, look at look at those jaws. You could stand up inside the jaws of the Megalodon.
Beautiful.
Okay, it is beautiful.
Wow.
I'm not coming at you though with a whole animal still attached to it. I can tell you that.
It's beautiful like that.
Yeah. Okay. I'm probably less likely to agree that it's beautiful. I think that it's just terribly frightening to think about the fact that these things actually existed. But the Megalodon shark was 50 feet long. And as I said, you could stand up in there, Tara. You know, you're pretty tall, and you could actually stand in there and not bonk your head on those teeth up there. Okay, that's how big this was. So you can imagine the amount of food it had to consume on a daily basis in order to keep its metabolism going, keep the energy levels up, right?
A few humans, yeah.
Yeah. You know, another giant ground animal at the time was the ground sloth. I actually just thought of the giant ground sloth. That was another one at that time. And they were very common, and then they weren't. So something happened.
They got eaten by the sharks.
Well, you would like to say that, except these aren't land sharks. These are ocean sharks, right? And the thing that happened apparently has been traced through examination of ground radioactive material that is in the layers where these things existed historically in the rock record, the fossil record. And it looks like the extinction rates in this layer are up to 3 times higher than any other time during this period, this era of time in the Cenozoic. That's a huge amount of time. So remember, like the Cenozoic, okay, is right. You know, if you look at the Cenozoic as in the era column, it's that orange column at the top there. And this occurred in the Pliocene. And so out there in the Pliocene, way over on the right under epoch, okay, of any other time in those orange periods that you see there, this era in the Pliocene, at this epoch in the Pliocene, that's when 3 times higher rates of extinctions were occurring. And some astronomers actually began tracing this to figure out what is causing this, what caused this. And it turns out that it looks now as if it might have been due to a supernova. A supernova that occurred near the Earth at the time. Remember, you have to remember the universe is always moving, right? The galaxies are rotating, stars are moving around the galaxies in orbits, and as they do that, one of the things that's really important is as they orbit the galaxy, you know, they're moving next to other stars, and those stars move away, then they move near other stars and move away. So over time, what we've found is that we have seen that we possibly have wandered too close to a star that obliterated itself. And this radiation, this deadly radiation that came off that star from that event could very well have bathed lethally the creatures at that time in the Pliocene epoch with a radiation that killed them. And so that is a theory right now that is holding water, so to speak, because many of the creatures were marine creatures. So I think that's pretty neat. So it's something that we can't rule out, you know. Now, you know, Tara, it was last week, I believe, or maybe the week before, and this takes us to our next thing. You actually said something that I thought was pretty interesting. You asked a question that was really compelling. And I'd like to take the time to answer that now. Okay. And Daryl will help on this one too, because I know he has some things to throw in here that are really good as well. But you asked a question, and it was really this: are there any universal numbers that you find in astronomy? Remember that question?
Right. I'm interested in that. Yes.
Well, there are many numbers in astronomy that are very universal. And I thought we should talk about that. Maybe this is, and so that's why you're one of the pictures right here. That's why you're one of these pictures. Okay, because you ask these really good questions. Okay, just so you know.
Thank you.
Yeah, no, and you know, we're not gonna, you know, we won't squeeze you out or anything like that. Okay, we'll keep you right nearby because we know that you ask good questions. All right. So you say that you say, well, are there any universal numbers? Are there any universal numbers in astronomy? And the answer is absolutely, baby. Okay, not baby to you, but you know, in general. Okay.
Right on, yeah.
Right on, man. So you say, well, okay, one of those numbers that's significant is the number 12. And I know that is something that might pique Daryl's interest. So I'd like to give Daryl the opportunity to tell us about the number 12.
Golly, 12 months out of the year?
Yes.
Yes, okay. Well, I assume you're getting at 12. I've said before, a month equals a month. Okay, a full lunar cycle is roughly a month. It's actually 29 and a half days, but one lunar cycle, a month, is where our word month comes from. And some of this is supposition on my part, but if you divide 360 days or 360 degrees by 12, you get 30. And the sun spends about a month in each sign of the zodiac, the 12 signs that are arranged along the ecliptic plane, which I hope to talk about after a while. And that sort of makes a year. Now, because the Earth doesn't go around the sun in 365 days even, but I think there's some correlation between why we decided on 360 degrees in a circle. Now, some of that might just be because 12 fits in there so neatly. It has so many different divisors. It divides so many different ways, you know. But anyway, I hope that's what you're getting at.
It is, in fact, and when we look at the zodiac, as you just pointed out, there's 12 constellations in the zodiac.
Yep.
And
Each one
13th?
is, I'm sorry.
There's the new 13th. How does that
Didn't
play
they add
into it?
the 13th? I thought they added one.
You're
off your
probably
camera.
talking about the constellation Ophiuchus,
Yeah.
which
Same.
again maybe I'll share later. When the sun is in Scorpius, the sun sign, when it's in the zodiacal sign of Scorpius, it's actually usually more in Ophiuchus than Scorpius, but conventionally we just say it's in Scorpius.
Yeah.
I'll show that in a little bit.
Awesome. Yeah, Daryl is going to be back with a wonderful planetarium, discussion about the coming stars, as we'll see in the springtime. Now, let's relate this whole 12 months thing and 12 constellations of the zodiac. Let's relate this to like exoplanets. There are some that are around these M-class stars, right? Now, the M-class stars are stars that are very, very low temperature, and they tend to be red. And we could do a whole show on doing a supposition of what life on such a planet around such a star might be like, because the planet's going to be locked like the moon is to the Earth. The planet's going to be locked to its star. These generally, the habitable zone of those stars are so close to the star that the planets are all going to be tightly locked. They're all going to move around, with the same face facing the star. But you have to ask, how long is a year on one of those planets then? Well, Mercury's year is 88 days long, because that's how long it takes it to go around the sun. And if we measure a year by how long it takes for a planet to go around its star, well, the year then for every planet in our solar system is different, right? And similarly, if we have exoplanets, some of these exoplanets around these M-class stars that are so low brightness and so low temperature that the planets can literally be just a couple million miles away and be in the habitable zone, okay, the year can be a few days long. Like there's some planets where where we found like a TRAPPIST-1. The year is no longer than something like 16 days, I think, on the furthest planet out from TRAPPIST-1. And so the shortest day is something like, in TRAPPIST, I think it's like 4 to 6 days. I can't remember the exact number. But if you think about it, that's their year. So that means that in the course of 4 to 6 days for the closest planet to the star, the sun, their sun, is going to go through all the constellations of their zodiac in 4 to 6 days. So how many constellations of the zodiac will they have? It's going to be really interesting to try and put that together. And would they even think of that? This is a cultural object, a cultural item, a cultural nuance that has been distinct and distinctly part of the human race because we just have a sun that is a G-type star, and we go around in 365 days. So it's pretty cool. But there's other things too that we can also talk about relating to those important astronomical numbers. Okay. One of them is actually something called the gravitational constant. Right? The gravitational constant is shown by the letter G, right? And I don't want you to worry about what you're seeing here on the screen, but I just want you to just see, okay, it's Newton's universal law of gravitation. Okay, this is the force. Don't worry about the equation. All I'm going to show you is objects that have gravity also have mass. Okay, and so it's the same. Okay, if you're massive or you have any mass, you have gravity. You have gravity as a human being. It's minuscule. We can't measure it, very well. But compared to the Earth's, yours is very, very, very tiny. All right, but you can measure the force of gravity based on your mass and the Earth's mass, and then figure it out. And the distance away of the masses make a huge difference. So like Earth and the moon has a mass and the Earth has a mass. And so the square of the distance away of the moon from the Earth gives us that force. However, what's G? That G is this gravitational constant I told you about. And this sentence kind of says it best. Gravitational constant, G, exists to give gravity the right magnitude and the right units. And the stuff in the lower right looks like gobbledygook to most of you, maybe, but don't worry about that. That's the actual value of G, 6.67 times 10 to the minus 11. But guess what? That number shows up in so many different calculations and so many different places. So it's actually a very important number in astronomy. All right.
Did you draw that diagram yourself?
I did not, actually. Yeah, I did not. But I was about to draw the diagram, and then I realized, wait, this one's saying everything I want, and it's a little more than I want to show, but it's okay, because I wanted to make sure that you understood. There's two masses have gravity of their own. No matter how much mass you have gravity if you have mass. And so the force of them can be measured by the distance between them. And you get a normal answer if you throw in the G factor. It shows up in many different calculations, many different equations throughout astronomy and physics, just so you know. So the next one that's a really important number, which I think is, of course, probably one of the more important numbers, is the speed of light. Okay. Light speed is something that, we didn't really know. Okay. Obviously. And, when we talk about the speed of light, one of the things that we want to think about with the speed of light is, how do we determine it? How do we know what the speed of light is? Okay. Well, if we look at the Earth here, we could determine that the speed of light is such that it goes 7.5 times around the Earth in just 1 second. So it's moving pretty fast. So when I tell you that Galileo tried to deduce the speed of light, but he failed, you can understand why. His experiment was to put a lantern on a distant hill and have the light blocked at a very, very specific time. And he would be doing timings as well. And when those timings were done, he figured if light was traveling at a finite speed, he'd be able to figure out the difference between the time that guy at the far, far mountain blocked the light and when he recorded the light going out. That difference in time would give him the speed of light. Well, guess what? He was on the right track, but woefully unprepared for the accuracy required to do the measurement. If you look at this picture, you can see 7.5 times around the Earth in a second. That is just something that, Galileo wasn't putting someone on a hill more than 4 miles away, maybe 5 miles away. So clearly he had little hope of trying to do that. trying to find it. So later on, when Ole Raymer worked on it, he actually showed that light moves at this finite speed back in 1676. And he did it by predicting timings of Jupiter's moons eclipsed by Jupiter, because the timings back then were actually quite good. And when people did timings of things back then, they discovered that, for instance, you could take you could predict Jupiter's moons to a fairly high accuracy. You'd know exactly when this moon was going to eclipse Jupiter and go behind it or whatever. You could actually know that really, really to a good approximation, really. So he noticed that the timings when Earth was closer to Jupiter on when Jupiter and Earth were on the same side of the orbit, that the timings happened a little bit sooner. And when Earth was on the other side of its orbit, farther from Jupiter, the timings occurred a little bit later. And it's from that.
Speaking of timing coming closer.
Yeah, yeah, you're right. We got like what, 30 seconds?
Nope.
Less?
Much less.
Oh.
We're in the minus. Work that into your calculations.
Oh, okay. Yeah. All right. Okay.
But we will have the conclusion on the other half, right?
Yes, we
Promise
will.
them that, entice them back.
Yes, we will. All right, guys. We will be back in just a few minutes. And I'm sorry for going too long. Commander. No worries. Anyway, we were talking about light speed. And I think that when Ole Rimmer actually figured out light speed using Jupiter's moons, he got pretty close, right? But he didn't have the equipment to really make the determination of what light speed actually was, okay? And so when Albert Michelson started looking at this problem, he was able to calculate for the first time the actual true value of one of these most important values in astronomy, the speed of light. And it is sort of like it's the speed limit, I guess you'd say, in the universe. And we know that we've been able to figure out ways to kind of do an end run around it, which is kind of cool. And that's something that probably in perhaps 100 years, 200 years, we might be able to utilize to get to the nearest star, not in 10,000 years like it might take us now, but maybe in 4 to 5 days, maybe a week. I mean, that's real possibility here. But, we have a long way to go, a lot of technology, and a lot of advancement to make first, But the actual speed of light, turns out, 7.5 times around the Earth in a second is at 186,282 miles per second. Now, in metric, of course, that's 299,792 kilometers per second. That's pretty fast. So you're not going to catch any photons with a net. I can tell you that.
Still in all, though, those are all based on those are all Earth-based measurements. They're not universal.
Well, that's based on the speed in a vacuum versus speed in water versus speed in air.
Well, I've talked about the metric system before, and it's really no more scientific than the standard or anything else. The French dreamed it up, and it works out to just under 300,000 kilometers a second. But still, in all, it's an Earth-based unit, and therefore, I don't think it's really could call it universal.
Well, everybody thinks so, but I guess in terms of the speed of light. The difference is so minor. It's not 186,282 exactly. It's point blah, 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 blah in this substance and blah, 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 blah in that substance. I mean, it does matter where you're emanating the light from and to, that's for sure.
Yeah.
But, as I promised, though.
Hey, we're Earth-based, so I guess we're kind of stuck with it.
Yes, we are. We are. However, we do know that the speed of light in a vacuum is going to be the same throughout the universe, depending on depending on what light's going through. If the light's going through a particular type of gas, well, there might be some differences, and that there are well-known understandings of what that does to light speed. And so, but the bottom line is you're not going to ever find light going 45 miles an hour. You know, you'll never find that. It's always going to have this very high speed. It's probably, again, the speed limit of the universe for that location is maybe a better way to put it, depending on the medium it's going through. Because the universe is not a vacuum, as many people say. It actually has stuff in it. There's atoms every few centimeters in the most vacuous of the vacuum. So there's no pure, total, true vacuum in space. See what I mean?
Well, yeah, but hey, I'm provincial. I'm an earthling, you know. What the heck?
Yeah, well, you know, lucky for us you are. I mean, I'm glad you are. You know, that'd be a bad thing if you weren't and didn't tell us. You know, we'd be working with an alien all this time and didn't even know it, you know.
Well, remember, my other name is Dar-El from Krypton.
That's right. Yeah. Yeah, and I'm only like Mayork de Triomphe or something. It's like, well, you know. Yeah, okay. Well, so, but you know, because I'm talking to you now, Daryl, I think maybe this is a good time for you to take us at light speed out into the universe to tell us about the springtime sky. And then we'll come back to these really cool astronomical objects. So I know you have to get that set up, so go right ahead and do your you can share if you want to do that and take us away to the universe of the spring sky.
Here it goes. Folks, I apologize. First time I've done this live, so we may have a few bumps in the road, but I've often talked about what's up in the sky, you know, various times, and we finally have a way to show it. Now, this is a web-based version of Stellarium. You just do a search online and you can find this. I find it to be very handy. I've tried to use heavens-above.com, but the image scale doesn't come across, so I do this one. This is my sky right now. No, excuse me, it's not right now. Or is it? This is my sky right now. Okay, the sun hasn't set yet. Some of this is everything's off by an hour because we went to daylight savings time today, so bear with me. I'm not used to it yet. I bet maybe most of you aren't used to it yet. So this view shows the sun is still up. Here's Mercury over in the morning sky. When you look at the sun, everything west of the sun is the morning sky. Everything east of the sun is in the evening sky. Now, I'm going to advance it until sunset. And here's what it's going to look like, 7:36 my time tonight. This is the sky over my location in Colorado Springs. I hope you can see the cursor and everything. We are moving from winter to spring, and a couple of the things I have set up on the screen, this green line running from north to south, running straight overhead, right about here, is what I've called the meridian in the past. This is the north-south line that passes straight overhead. At sunset, this is the division between the evening sky and the morning sky. I'll back up for just a second. And okay, then we'll go for it just a little bit. The sun just set. Basically, at sunset, the division between the morning and the evening sky is over on the horizon at sunset. At midnight, the meridian becomes the divisor between the evening and the morning sky. When I talk about planets or the moons or the moon at opposition, at midnight, the moon will be right about here, and planets will be right about here at midnight. They'll rise at sunset, they'll set at sunrise, and they'll be nearly overhead at midnight on the red line, which is the plane of the ecliptic. that highway in the sky I've talked about. The plane of the ecliptic, this is the path the sun makes in the sky from Earth's point of view. Basically, this defines Earth's plane, orbital plane in our sky, centered on the sun. Now, all the planets also tend to stick really close to the plane of the ecliptic, and the plane of the ecliptic is also where we have these zodiacal constellations, Pisces, Aries, Taurus, Gemini, Cancer, and Leo right now. And then Virgo is going to come up over here in the east in a little while. You might remember last October when Mars was in opposition, it was over here in eastern Pisces. Well, we passed Mars. Mars went back into direct motion, and Mars has been racing to keep up with this, though it is slowly falling behind. Mars left Pisces. Mars went through Aries. Mars is now in Taurus. Last week, this is the Pleiades, the Seven Sisters. Mark has shown you many times on SkyTour livestream. It's the really beautiful star cluster, M45, Messier 45. Mars passed the Pleiades last week and is now drawing really close to the eye of the bull in Taurus, where my pointer is. That's the star Aldebaran. If you have a clear sky and go out and look tonight, it's a striking view that they look almost identical. It's like Taurus almost has a twin up there now. Mars is going to continue. It's going to pass Taurus in a few days. It's going to go through the horns of the bull. I'll show you the figures here. Okay, here's the head of the bull, the Hyades star cluster. Here are the horns of the bull. Mars is going to continue marching through the horns of the bull and enter Gemini. It's going to keep racing to keep up with us, but it's going to fall slowly farther and farther behind as we speed ahead of it as we go around the sun. Anyway, right now we are in late winter. We're almost entering spring. And here are the stars of winter. They're already almost all west of the meridian, you see. So they're in decline now. And I'm going to change the time. You'll see that, excuse me. Again, this is my first time here. You'll see Orion is setting by about 11:40 at night. One more hour, and Rigel has gone away at a little after midnight. And all the other bright stars of winter are also going away. Here is Sirius. You may have heard me talk about the winter hexagon or the winter circle, that you start at Aldebaran, you go up to Capella in Auriga the Herdsman, then you have Castor and Pollux in Gemini, down to Procyon, on to Sirius, and then to Rigel. If you go out and look, this makes a large asterism in the sky. It's kind of an oval shape. Some call it the winter circle, but it's more of an oval. And you see that it's going away now. By 11:30 now, 11:40 with daylight savings time, Orion is getting ready to set. So is Sirius. In another hour after midnight, you see they're about to set. So anyway, my point is that there go the stars of winter. And here comes the stars of summer. The stars of spring. Ursa Major, the Big Dipper, the Big Bear is up now. Leo is up. Virgo and the bright star Spica and Boötes the Herdsman and the bright star Arcturus are well up before 10 o'clock at night now. This is at 9:42 my time. And here comes springtime right there. So that gives you something to look forward to when you look up in the sky. And if we keep marching through the night, there's after midnight, you see Ursa Major is already crossing the meridian, the Big Dipper is. There is Polaris, the North Star, tip of the handle of the Little Dipper, Ursa Minor. Ursa Major is already past the meridian by a little after midnight. And here comes Virgo, here comes Boötes and Arcturus. And here comes the stars of summertime. Hercules will be up. Serpens will be up. Ophiuchus will be up, which I'll talk about more in a minute. and Libra down in the south. And hey, Vega, it's one of the harbingers of summer. It's the westernmost star in the summer triangle. Vega is up, well up, by midnight now. And if we carry on till about 4:30 in the morning, 4:45 in the morning, well, the stars of spring are now west of the meridian. They are in decline. And here comes all the bright stars of summer in the morning sky. We have Scorpius, we have Ophiuchus, and hopefully this is what Tara was referring to about the 13th sign of the zodiac. If you follow the ecliptic this time of year, this time at night, you see that it's just barely grazing Scorpius, and it's actually in the southernmost Ophiuchus about as long as it is in Scorpius. But conventionally, because 12 goes so easily into 360 and all sorts of other numbers, 24 hours, etc., we say it's in Scorpius, even though it may appear more likely to be in Ophiuchus. And here comes the teapot in Sagittarius. See the teapot there? There's the handle, there's the top of the lid, and there's the spout of the lid. There's the tip of the teapot, tip of the spout. Now, just right over here, that's the center of the Milky Way galaxy we've talked about before.
That's where a supermassive black hole, the center, is sitting. And we got a 10-year study which showed the stars orbiting that black hole.
Yep. And by 4:44 in the morning right now, well, there's Vega, there's Deneb in Cygnus, and there is Altair in Aquila, the eagle. You see the wing spread. Altair is the eye of the eagle. And there's little Tarazed, that's the top of the eagle's head. That's one of my favorite stars. You can see the eagle there. But that is the summer triangle. So summer is on the way, and spring is almost here.
Can't wait.
Yep.
Cool.
I hope you enjoyed that. I'll probably delve further into this in future episodes.
Oh, you darn right you're gonna. This is great stuff, Daryl.
But
Great stuff.
This is our sky right now, just well after sunset.
And thank you, Laura, for saying that. We really like that we can do this all visually now.
I hope so.
Yeah.
That's a wonderful feature to have, yeah.
Yeah. And Mark wants me to teach this to you, Amanda.
That's right, I do.
Does
Because I
it?
want Amanda to talk about the mythology of the constellations.
Ooh,
Hey, look, we
is
have a
that a
satellite.
fact?
We have a satellite going through in a couple of hours, too. That's a satellite right there.
That's right.
See how it's moving from south to north? It's in a polar orbit.
Wow.
And there's Amanda's Gemini right there. It's the two brothers.
Yay.
Casper
Side by
and Tom.
side, shoulder to shoulder. I've seen them portrayed with their arms over each other's shoulders. There's Castor and there's Pollux. You can always tell the two apart because Castor is closer to Capella, C to C, and Pollux is closer to Procyon, P to P. So you go Capella, Castor, Pollux, Procyon. That's how you tell the
Nice.
twins apart. And I was a twin, so believe me, people have trouble with that sometimes. That's how you tell the two apart.
Okay.
Castor, Capella, and Pollux and Procyon. And
Nice.
I said enough.
I'm actually enjoying it. It's like watching a movie, right? I mean,
Yeah.
No, a lot of people are.
That was
Kathy's
great,
giving you shout outs. Ronald's giving you shout outs.
I hope you
Cool.
folks enjoy it. I mean, people are really enjoying it. And the comments you see on the screen are only the ones that we can actually grab and pop up on the screen. But there's a lot more out there. People are enjoying it, Daryl.
We will delve further into all this. And
Absolutely.
Wonderful.
I'm going to end it for now.
Alrighty.
Okay. So,
Here we go.
ta-da.
Ta-da. Well, thank you, Daryl. Clap, clap, clap. The way we laugh and clap, it's called clapter. See? So, and just before that, we had been talking about these crazy numbers in astronomy that are very important in astronomy. And one of the others that turns out to be something that not many people really know about is a number that's actually called the ideal gas constant. What is that? Well, it really comes from the find that temperature is found to be proportional to pressure and volume. And this makes sense. If you have a balloon and you squish it down, you're trying to change its volume, but you still have the same amount of air inside that balloon. It's going to get warmer. So the temperature is going to rise. And that relationship formalized, okay, it looks like this. This is actually what it is. And again, this isn't a show about doing equations for you guys, but I'm trying to illustrate if the pressure goes up and the volume stays the same, then in order for these things to be equal, the temperature has to go up. And to keep everything right, in order for it to work, you have to put in this thing here. It's R. R is called the gas constant. N is the number of atoms of a material. So that changes. But R, okay, that's a gas constant. So this equation, which some of you remember from your chemistry classes, PV equals nRT. I remember that. Okay, this is the ideal gas law. And so basically it shows that pressure and volume are related to temperature. That's the most important part, most important thing here. Okay, so you'll find also that because of that proportionality, that this opens up the entire spectrum of abilities for you to do calculations on gas out in the universe, out in space. Okay, we talk about these things, and it's really, really important. So the whole concept of the ideal gas law and this whole concept of having these constants that become very important in astronomy is something that we can't escape. You know, another one we can't escape is actually related to this one here. Okay, what is this? Well, actually, this is just an illustration showing measurements of molecules that are warm and molecules that are cold. Can you guess which side has the cold molecules?
I would say the blue side.
That's correct. Okay. On the right-hand side, when there's warm temperatures, the molecules can be bouncing around each other and banging into each other and stuff. And that's actually that collisional process that we're seeing there, right? That causes these things to actually be very, excitable, and they move around a lot more. They take up more space, all right? And so if you chill them, you cool them down, and it goes further to the left. And by the time, yeah, well, go ahead, Daryl.
Oh, I'm sorry. When you get to absolute zero, I assume there on the left end would be dead flat.
Actually, it's not, although it's close. But absolute zero is, in fact, the area where here on the far left of the image, which we're getting to. And if you go down that, you go from hot to cold. When you get to absolute zero, which is right here on that left side, this is the place where the molecules move the least. But they're not ceasing their movement. They're moving the least at that point. Okay? And what is absolute zero, and how does it relate to like our temperatures? Well, this kind of gives you an idea. Okay, this particular indicator will show you. On the left here, we have a regular temperature. All right, this is Fahrenheit on the left. In the middle, we have Celsius, and on the right, we have this thing called Kelvin. When you're talking about absolute zero, you typically are talking about a Kelvin scale. And it's not degrees Kelvin, it's Kelvin. That's what we're talking about. The number itself gives us all the information we need. I don't know where the degree indicator came from in the past. I don't know that it's necessary. But if we look at water boils at 212 degrees Fahrenheit, 100 degrees Celsius, and 373 Kelvin, water freezes at 32 degrees Fahrenheit, 0 Celsius, 273 Kelvin. But then down here is where absolute zero is. Minus 459 degrees Fahrenheit, minus 273 degrees Celsius, and that's 0 Kelvin. There is no minus 10 Kelvin, okay? There's 0 Kelvin. It's the least of the numbers we can have on the Kelvin scale.
It would be fair to say that Kelvin, the units are still they're equivalent to Celsius scale wise.
Well, yeah, it's minus 273, plus 273. Okay, Kelvin plus 273, okay, is going to be Celsius, I think. So when we look at, for instance, at like 0 degrees Celsius, you have to subtract 273 to get to Kelvin. So Celsius minus 273 is Kelvin. Okay, so that's kind of what it is. And to get to the Celsius temperature, you would add 273 to the Kelvin. And Fahrenheit is the weird one, okay, that just doesn't convert nicely. But because of metric system, this converts very nicely between Celsius and Kelvin. I know you're not a fan of the metric system, Daryl, but in this case, in astronomy world, we talk usually about Celsius and Kelvin. We never talk about Fahrenheit.
Yeah, I won't go there.
Well, that's okay.
I believe in King John's thumb, okay?
Yeah, okay. I remember that. Yeah. So that all said, okay, the concept of absolute zero is something that is extremely important. Again, everything vibrates in the universe. Everything vibrates. Everything's in motion. I've said that before. But that point where there's a bare minimum of motion at all, that's the place where absolute zero lives. Okay, and so that's what it is. That's what absolute zero is that particular location, that particular spot.
And if you consider the cosmic microwave background radiation that, is like what we see as the edge of the universe, I suppose, that is only, what is it? It's like 2.7 4 degrees above absolute zero.
Yeah, it's just, it's like, it's literally just a 2.7 or 3 degree Kelvin background radiation. I keep putting my hand over my face. Sorry. Some people want that. And that's correct. And that actually is another thing we'll come to, because that actually figures strongly into some of the important numbers in the universe, in astronomy, Now, earlier when we talked about the black holes and stuff, this is an image of an artist rendering of what a black hole might look like. But interestingly, this is sort of kind of what they really do look like. If you remember the image from the Virgo supercluster and looking at M87, that galaxy, they imaged the supermassive black hole at the center of that galaxy. And it turned out that black hole was just immense, but on top of that, the shape and how it looked was predicted, and the result that they got was exactly what was predicted. It couldn't have been a better match to our relativistic predictions. Couldn't have been a better match. It was really, really good, But black holes have a certain size, a certain radius, okay? And it is called, the actual thing it's called is the Schwarzschild radius. And the Schwarzschild radius is a value that you can use to calculate the actual size of a black hole for a particular mass and so forth. And I think that in our universe, we use that to work with black holes and to calculate how big a black hole is going to be. Now, a black hole has an event horizon, right? The event horizon is the area where in the picture you see the black giving way to stars and that little white ring around it, kind of, sort of. That's the event horizon.
And like a black hole has an event horizon, our radio show has a commercial break.
Okay. Hey, you know what, folks? I tell you, I just get carried away. This stuff is so cool that thank God for Amanda, because she's keeping me on track. I am sorry. So, Amanda,
well, you can tell he's not faking it. You can tell he loves it, and that's why it's infectious, and that's why hopefully you'll join us after this break.
I'm sure they will. Thank you, guys. We'll be right back after this.
you intrigued by Paranormal Talk Radio? You'll love the new Paranormal Radio app from TalkStream Live. You'll find a great selection of talk shows covering UFOs, ghosts, strange phenomena, and much more. Download the Paranormal Radio app now and start listening to the very best in paranormal talk entertainment, including the network you're listening to right now, the Paranormal Radio app. Free in Google Play and the iOS App Store.
Are you still at it?
Yeah, I need more speed.
This baby's fast.
My dad's fast. He's scary fast.
You really think you could beat him?
Yeah, because I drink more tea than he does.
Yeah, right.
You know, pal, it's the tea that makes you go. Oh. Hey, Dad. You know, kiddo, you have to drink a lot more tea to be faster than me.
Drink the tea that makes you go. Life Change Tea. You may not need as much as Dad. You never know. GetTheTea.com. Log on to GetTheTea.com.
Welcome to the new KGRA digital broadcasting website, thekgradb.com. Here you'll find great new content, including the KGRA Classics, great shows from our archives. You'll be able to see the show times and information so you can see what show is currently on air. The on-air live button. So just go to this section and you'll be able to hear the show live with exceptional sound quality. We also have the Vault section. Make sure to subscribe to get access to great content and special features. We have the main content for our latest news and events, so make sure to sign up and you can be part of our forum. So make sure to check out the new KGRA digital broadcasting website, thekgradb.com. We look forward to seeing you there, and we hope that you enjoy the new website.
Mainstream media's most wanted. KGRAradio.com.
Well, we're back, and we're stuck in a black hole here, but don't worry, we're out of it. The thing that's interesting about the black holes that we were talking about a moment ago is that horizon that they have around them. When you say light can't escape a black hole, that gives rise to the wrong thinking process, I believe, because a black hole doesn't bend light. It doesn't. They say light can't escape. Even light can't escape. They make it sound like light is being altered by the black hole. It's not. The black hole isn't altering light. It's a two-step process. The black hole is changing space. I know, that's a tough one. You consider it like the fabric of space, all right? So a black hole takes space, all right, and it'll do this. A black hole will bend space, all right? And light dutifully follows space, so it follows the curve of space. As far as light's concerned, it's always going straight, okay? But because space is bent by the black hole's gravitational structure, gravitational well, as we call it, then light will follow that curvature of space. So that is actually what's going on with black holes. They bend space, they warp space, and light just follows that, like a car following a hill. It goes up the hill, it goes down the hill. The car doesn't go through the hills. It goes over the top of the hill. Well, if the car is an element of light, a photon, and the warped space of the hills, well, you can see how light will follow the curvature of space. And if that curvature is bent enough, then light will go inside the object and just stay in there because it's staying within the curve, and the curve is closed inside, and now the light can't ever get out. So that's what they mean by that.
This is where so-called Einstein crosses and such also come from, correct? Where we will look at a galaxy far out in space, and we'll see several light points of light or images, almost like multiple images around this galaxy of something that's behind it. And,
yeah, you're talking about
the most famous,
lensing.
Yes, gravitational lensing. And a couple of famous examples, I think they call them Einstein crosses.
Yeah. Yeah, and Tara asked a question that is in her list, I think, that relates to this. And it relates to these radio rings. Do you remember that, Tara?
Are you talking about if black holes have hair? Is that the question?
No. Don't worry, folks. We're going to talk about that. Don't think black holes have wigs or anything like that. No, you were asking about there were these radio rings that were seen out in space, and no one could understand what these rings.
Oh, the odd radio circles.
Yes.
Yes, those are the coolest things.
They are
so cool.
Right, and I have a theory as to what they are, and I have done no research on these yet, so I could be totally wrong, and I'm okay with that, because as a science guy, you don't get upset if you're wrong. You just look at it and you figure out, okay, what went wrong? Let's figure it out. I think that we're seeing a gravitational lensing event, but in the radio realm. So in other words, as Daryl was pointing out, let's bring our black hole back. Okay. If you're on the other side of this black hole that you see in the screen, as say a star or a galaxy, then the light will get bent by the gravity of the black hole that's coming toward it from the far side, and it'll end up making what looks like a ring around the black hole. We've seen a lot of really interesting structures like that are like rings, and they're actually these lensed objects, and sometimes the rings are incomplete and just partial rings. You can see galaxies that are shaped like little shapes like this, like little curves, and they really should be flat, but they're curved. That's because they're getting bent because they're at a certain proximity from the black hole. Farther away they go, the less they're going to be bent. The closer they get, the more they're going to be bent. So it's going to be like that the closer they get, if the black hole's in the middle here. So I think that these odd radio rings are going to possibly turn out to be lens events that are caused by black holes and radio emissions farther beyond them, because it's just light. So we can expect to see rings in the same way that we see them with the gravitational lenses. That's what I think. So we're going to see where the research takes us, but it's just a thought process I've had. I've never gone into it though to understand. So if I'm totally messed up about it, I apologize ahead of time. Okay.
But isn't it that nobody understands what they are at this time?
Yeah, I mean, I'm just
yeah,
a supposition.
So I think that's really cool. It looks like big pasta to me. It's like the edges are real fuzzy, and it's like it's been overcooked or something. They're just really cool.
You didn't eat dinner tonight yet? Is that the idea? Because
that's a lot of pasta.
That is. Yeah, no, that's cool. Based on what we're seeing, I think that maybe that is a lens event. I can't tell you for sure, though. Daryl, I don't know if you have any thoughts on it, or Amanda, but I'm happy to hear your thoughts.
If you put that black hole image back up,
I will.
It could be conjectured that the object at 4 o'clock and the object at 10 o'clock are the same object seen twice in a gravitational lens.
Possibly. The only difference is that the objects at 4 o'clock and 10 o'clock might actually be curved and flattened a little bit, because the lenses tend to distort the objects. But don't forget, and you know this as well as everybody that listens to Sky Tour live stream, stars are always ever just points of light. As bright as that object at 10 o'clock is, it's just a tiny point of light compared to the smallest point of light you can see on the screen. All right. And it's hard to understand until you put into perspective of how much light is coming from it. The amount of light coming from that is what determines how big it appears on a photographic sensor. But it's really just a tiny point of light, and we would expect it to be smeared a little bit.
Yeah, and this is the case, such as with the Einstein crosses, that what you're saying behind that galaxy or that galactic cluster is a whole other galaxy or galactic cluster, and it has dimension and size, and it's often stretched.
Yeah.
There's a famous image out there, which I won't try to go find right now, but you're seeing several duplicates of the galaxy or cluster behind the foreground object, and they look similar, but they don't look the same because they have been stretched and warped and altered by the gravitational well of the foreground object.
That's correct. That's correct. And before we go further, I just want to talk to Amanda. Amanda, were there any questions so far that we may have missed that we probably should discuss before going further here?
Oh, yeah. Some are going way back though, guys. Okay, one of them was Ojo. Hopefully I'm pronouncing that right. I was wondering if there's some kind of energy field that holds comet debris that become meteors. It seems the energy field can alter tectonic plates, causing earthquakes.
Okay, that's Ojo. Thank you.
Going back from earlier, sorry.
No, it's okay. Ojo, thank you for that question. I think my feeling about that is that when we look at our solar system and we look at where comet debris is and where comets might be, one of the things that we notice is that we have certain areas in our solar system where some of this stuff is sort of stored. And I mean by that, in orbit around the sun. Some of it's closer, like Mercury's very close to the sun. Some of it's farther away, like Pluto. But beyond that, we have a belt of objects that are asteroid/comet-like. That's something called the Kuiper belt. And Kuiper is actually spelled Kuiper. Go figure. And the Kuiper belt has things that could become comets if they get close to the sun. And then beyond that, we have the Oort belt and the Oort cloud, and that's Oort, the Oort cloud. And that is the realm where a passing star might come through the galaxy and over millions of years dislodge and move a little object up there, and it starts on its very, very long journey, and it comes down into the solar system where it becomes a new comet that we see. Oh, look, here's a comet. And that's how those things come in. So the energy field you're talking about is really no more than the gravitational field of the sun holding these things in its presence, basically. And as far as tectonic action, we don't see any effects from off the planet that can alter the geology on our planet other than the gravity of the moon itself and the gravity of the sun, which is affecting the Earth next largest relative to the Earth itself. The Earth is actually pretty dynamic on its own. It doesn't need external forces to really start moving things. But the tectonic plate action is really mostly generated in fact, almost entirely generated from the activities inside the Earth itself. Giant crustal plates that are crashing against each other and sliding against each other and going this way and that way against each other. Some are going up and down, right? And they actually cause earthquakes and things like that. So it's not that the energy, there's this mystical energy field out there, and this leads to people saying, well, what about Nibiru and all these other, planets from out there that we know are there? No, we don't know they're there. We actually don't have any evidence that they're there. We have evidence that there's larger bodies out there, but when we say large, we don't mean many times the size of the Earth. There's objects out there that have more mass, yeah, but they're all small. Generally, I mean, there is some thought about a Planet 9 out there. But when we say Planet 9, even that is something that's not going to be much larger than Pluto. So we're talking about a lot fewer objects out there that are Earth-sized at all. Keep in mind. Go ahead.
I'm sorry. I thought some of the speculation about so-called Planet 9 was they thought it was maybe about 4 times the Earth's mass.
I saw that, but there's really no evidence of it now. I mean, they have some speculative theories about it, but we would see effects on Uranus and Neptune and Jupiter, and so far I haven't seen any papers that indicate that they're having any kind of influence like that on them. Something 4 times the Earth mass would actually kind of show up in the solar system. Now Jupiter is much heavier than that, still much more massive, I should say. But we would see something out there that's causing these what we call disturbance or perturbations to the outer planets. And so far, I've seen no papers that show any of that. But it's possible that from a potential perspective, you can say, oh, it's possible. But
I thought there were some far-out objects, Kuiper Belt or Oort objects that seem to show a certain resonance in their orbits that which is what led them to the putative 4 times Earth mass object they're looking for out there.
Yeah,
we talked about this before.
Yeah, and I'm not convinced that that's actual as opposed to just normal for those conditions out there. But things change. Like I said, I know I'm not right about everything at all by any stretch, but I am very curious. So I would love to know what's going on out there. I'd like to know the truth of what's going on out there.
Yeah.
Yeah.
There's another question Daniel Whitaker asked. Amanda, would you mind popping that for us?
Yes, definitely. He wants to know there's a 1 kilometer near-Earth object coming to its closest approach on March 21st at 5 lunar distances. Are there any plans to try and see it? Our producer, Bill Skywatcher, also does Skywatches, hence the clever name. Maybe he could chime in private chat. We could pass that on. Do you know about it?
This sounds like the god of chaos that Tara talked about last week.
Apophis.
The asteroid Apophis. It's going to be closest on the 21st of March, I believe, and they say it's actually going to be bright enough you'll be able to see it naked eye. It'll be as bright as a third magnitude star, which is a Midland bright star. It won't be really bright, but it won't be really dim either. And you'll actually, I believe it's going to pass closest to Earth while it's still daytime here in North America. But Europeans ought to have a prime time view of it. You'll actually be able to see it moving across the sky.
And it moves quite fast. I mean, you're not going to, it could be mistaken for a satellite in the sky potentially, because some of these things move at a rate that's really exorbitant, and depending on how close they are to the Earth, that determines a couple things: the speed at which they transit our space and you go through our space, and how bright they appear. But most of these are very dark. So the fact that it's going to be magnitude 3, which is fairly bright, okay, shows that it's actually going to be quite close. And 5 lunar distances.
I was just going to get to that. That's why I didn't drop the question yet. I mean, I could take a pretty good guess at what 5 lunar distances means, but can you tell us just to make sure?
It's 5 times the distance of the moon from the Earth.
Okay. And that's as straightforward as you're going to get from astronomy, because usually they make it tricky and weird and Latin and everything. So
a million miles.
Million and a quarter miles.
Yeah.
And it's still bright enough for us to see naked eye. That is pretty remarkable.
Yeah.
That is pretty cool.
Well, its size makes a determination of that as well, okay, besides its composition and what it's made of. Apophis, what's the size of Apophis, Darrow? We talked about this, and I can't remember the size offhand.
I thought you said like 900 feet or something.
Yeah, it's not that large. But it's big enough so that if it's catching the sun, we'll see it for a period of time. And I don't know how many degrees of sky, it'll cover in what period of time. So I'm not sure of its speed through the sky.
Interestingly, the next time Apophis is due is 2029 is the one where they used to think it might hit Earth, and they say now it's going to miss. But interestingly, it is going to come close enough that it will graze the geosynchronous Earth orbit area.
Yeah. That could be dangerous for some satellites that are out there in geosync orbit.
Yeah.
But nevertheless, that's cool, Amanda. If you got more, let us know.
There were a few more earlier, but they've kind of been answered already. One was, would physical formulas on Earth still work in outer space? I'm guessing they would be. You just changed the formula for its orbit and gravity and all that good stuff, right? Fill in all those letters.
Some equations will work fine in orbit or out in deep space, but some won't because they depend on things like pressure. And so any formula, for instance, that uses temperature won't work in deep space because there is no temperature in deep space. But wait, Mark, you've said that the temperature in space is not minus 400 degrees or whatever. Yes, but that's only of something capable of capturing radiation and receiving this radiant energy from a star. It absorbs this radiation. So anything that you see in space, we measure it not by temperature, okay, but by its ability to absorb radiation and emit radiation. Yeah, I know. That's taking you down a whole nother rabbit hole. I get it, guys. But
It's a lot, Mark, yeah.
But the fact is, okay, when we talk about temperature depends on the, for instance, I'll give you an example. On the moon, you have to have something, for instance, that can absorb the radiation from the sun. So it makes logical sense to say the soil on the moon will be a certain temperature in the sunlight, and that same soil on the moon will be another temperature when it's the lunar night, when it's part of the cycle where the moon's in shadow. Okay? That makes sense. But you can't be this far above the moon, literally an eighth of an inch, and say that you can feel temperature. There is none. You won't feel temperature. You could be a 16th of an inch off the surface of the moon, and there's no temperature that you're feeling. All right, what you feel is any radiant energy that's reflecting or radiating off the moon, like infrared energy, heat, after it's been heated, that strikes your finger, say, and heats up your finger. Your finger will then have a temperature. There's a distinction, and it's an important one. We have to talk about those distinctions, you know. So that's why things like the ideal gas law, where pressure times the volume equals the number of stuff times some constant times the times the temperature, those things wouldn't exist on the moon. You can't use that on the moon or in space. It doesn't work. There's no pressure. There's no temperature. You need to replace those with something, as you were alluding to, Amanda, you need to replace those with something more meaningful for space. And in terms of pressure, maybe you're talking about the number of atoms or the number of, let's say, rays of radiation that are striking a surface per unit time. Okay, maybe that's the pressure. And the temperature might be inside the soil. What does that radiation do to the soil? Does it heat it up? That would make sense. But in space itself, where you have so few atoms in space that to talk about a medium through which temperature can propagate, like air, okay, it doesn't exist. So all we have in space is absorption and radiation. And those are the two magic things we do in space, right?
I have seen it addressed occasionally in science fiction. One of the realities of manned space flight in the future is we're going to have to get rid of waste heat. Mm-hmm. And sometimes sci-fi authors, they will put big radiators on their spacecraft. They don't have conductance. They don't have convection. All they have is radiation to disperse that waste heat. And sort of like how we put radiators on cars to get rid of the engine heat, they're going to have huge radiators on the spacecraft, which would just be big fins probably, with a cooling solution running through them, that they will run that coolant through and disperse the waste heat.
That's right. In fact, the International Space Station has radiators on it as well. Uh-huh. And they're pleated things that sort of unfold, and they accordion out, and you get these long, weird-looking things that look like that. They go up and down, and they're square, and they kind of go up they look like dominoes lying side by side or something, and kind of with a little crook in their path. And those are actually the radiators that are radiating the waste heat. Uh-huh. And again, that's because of what we're talking about, just as Daryl's saying, absorption and radiation. So you're absorbing all this energy from the sun, and you got to radiate it away, all right, to maintain your proper temperature. That's why when they dock the Soyuz spacecraft to the International Space Station, by the way, what do? One of the first things they do after they get out is they do what? They put a giant hose down inside of it. and they put air down there. They're running air. Why? Because the spacecraft is like a little oven. It's going to unchecked, unmetered, unregulated. It's going to heat up and get really, really hot from the radiation that's hitting the outside of the space capsule and causing it to absorb a lot of this energy. So they have to cool it. And so they have to run air through it. They do that all the time. That's why you see those big tubes running down into all the connections in the space station. When I was younger, I thought, what are they going to do with them tubes? Because I see the tubes going through openings. It's like, well, what if they have to close the opening? The tube's in the way. And it actually is. So if there was a real disaster, that tube could be a huge problem. But they have to cool and regulate temperature of everything in the space station. So same thing. And incidentally, that Soyuz, there was a Soyuz docked to the space station recently, and when they did all that and they had everything, equilibrium, they noticed that they were losing oxygen on the station. You remember that, Daryl? I think you remember that.
Yes.
Yeah, and this indicated something on the station is losing air, and they thought, did we get hit by a micrometeorite? And now there's a hole in the wall of the station somewhere. Is there a problem with one of the spacecraft attached to the space station? And they went through to try and find this. And only through a process of elimination were they able to discover that the Soyuz that had docked, the Soyuz capsule that had docked, had been worked on the ground. And a technician accidentally drilled a hole through the outer skin. Oops. I mean, to me, that's like...
Ruh-roh.
Yeah, ruh-roh. Yeah, ruh-roh.
Scotch tape or bubble gum.
Yeah, and I think that's approximately what they used to fix it on the ground. And when it got up to space, of course, that failed after a while, and a tiny bit of oxygen was escaping. The other problem you have in space with something like that is that if you have something that's leaking air, that's like a little jet. And that little jet can cause changes to the motion. So if you're traveling along horizontal like this, okay, and all of a sudden, you get a little jet of air coming out of one side of you. We won't go into how that could possibly happen. All of a sudden, you're going to go, and you're going to go like that. You're going to start tipping, and you're going to keep going because there's nothing to stop you unless you send a jet of air the opposite direction and make you slow down and stop. Okay, but see, that's something that could very well happen. And so if the Soyuz, for instance, let's suppose that the entire Soyuz capsule failed and the air from the Soyuz got blasted out into space. That's like a big giant kicking the space station ever so slightly, and all of a sudden the space station is going to go, it's going to change its orientation, and they're going to have to get that back.
Is it going to sound like that too?
Exactly like that, actually. Precisely like that. That's the sound of the Soyuz evacuating air.
Good.
And people can visualize that maybe during our break.
Oh, the break.
I know. I hate to be the bearer of bad news. No one's going to like hearing from me anymore.
No.
The only time I pipe in is to take another break.
You're fine. And I don't understand why. Okay. You know what, folks? I love doing this so much that I totally sometimes ignore the breaks, and I have to apologize. If you want me to go away and have someone else do the show, just let KGRA know, okay? And
then you'll know if our email's still working. All the spam messages. You got a half hour left. Get those fingers moving, folks.
Yeah. See, Amanda wants her show, and I know she should have this show. She have it. Go ahead, Amanda. You can have it. Folks, we'll be right back after this.
Are you intrigued by Paranormal Talk Radio? You'll love the new Paranormal Radio app from TalkStream Live. You'll find a great selection of talk shows covering UFOs, ghosts, strange phenomena, and much more. Download the Paranormal Radio app now and start listening to the very best in paranormal talk entertainment, including the network you're listening to right now. the Paranormal Radio app, free in Google Play and the iOS App Store.
Are you still at it?
Yeah, I need more speed.
This baby's fast.
My dad's fast. He's scary fast.
You really think you could beat him?
Yeah, because I drink more tea than he does.
Yeah, right.
You know, pal, it's the tea that makes you go.
Oh.
Hey, Dad.
You know, kiddo, you have to drink a lot more tea to be faster than me.
Drink the tea that makes you go. Life Change Tea. You may not need as much as Dad. You never know. GetTheTea.com. Log on to GetTheTea.com.
Welcome to the new KGRA digital broadcasting website, thekgradb.com. Here you'll find great new content, including the KGRA Classics, great shows from our archives. You'll be able to see the show times and information so you can see what show is currently on air. The on-air live button. So just go to this section and you'll be able to hear the show live with exceptional sound quality. We also have the Vault section. Make sure to subscribe to get access to great content and special features. We have the make content for our latest news and events, so make sure to sign up and you can be part of our forum. So make sure to check out the new KGRA digital broadcasting website, thekgradb.com. We look forward to seeing you there, and we hope that you enjoy the new website.
Mainstream media's most wanted. KGRAradio.com.
Welcome back to SkyTier Radio. This is Mark D'Antonio, your host who knows not when to quit. I can't help it, this new medium with video and visual stuff, it's just so
cool.
Enticing. Yes, it's enticing, Tara, to do all these crazy things and do fun stuff. And so I get started and I got to end. And it's not, Amanda, that's nothing against Amanda. Amanda's doing the right thing. She's doing exactly what she has to do to keep me doing what I'm supposed to do, But what I'd like to do, though, is I'd like to have Tara ask some of the questions that she has come up with for us tonight in this final half hour. And I'll try to make sure that I pay more attention to everything else going on.
Okay. Mark, you were talking about gravity and stuff. I'm wondering if you can explain what the different forces of gravity are, and do they all have to exist together, or how do they work together, and what does that mean for our ability to go into space or onto another planet?
You're talking about the different forces. When you say different forces, you mean the nuclear forces? We have the strong force, the weak force, and gravity is the weakest of the forces, right? But oddly, it's the weakest, which is kind of interesting. We have. I'm trying to figure out what exactly you mean. I'm not quite sure.
Well, you're talking about gravity and being able to measure gravity, and we all have our own gravity. And I thought maybe I heard that they've just weighed the gravity of a ladybug or something. And I'm just curious that how, if we're going to be in space, we're not subject to gravity. And so how is that going to affect us? And so what is artificial gravity then? Do we have to make gravity to be in space? And
oh, I see what you mean. Okay, yeah.
And do we have to have all these forces on us?
No, okay. I thought you were going down the path of the electromagnetic force, the strong force, the weak force, and gravity. But you're talking about something a little different, which is actually less confusing. You're asking, when we go out into space, for instance, okay, we have our own gravity. That's true. Okay, so if we go out into space all by ourselves and we go far away from anything else that can influence us gravitationally, if you take a spoon, a metal spoon, and put it 10 feet away from you, okay, it'll take a long time, but eventually that spoon is going to come and go and like stick to you, okay, because of your mutual gravity. In the same way, we see asteroids that actually illustrate this concept very, very nicely. They're giant piles of rubble that just happen to be just nestled together and going around the sun as a rubble pile. And actually, they're called rubble pile asteroids. You know, Bennu might be a rubble pile asteroid, for instance. See? So at least that's gravity-wise, that's what happens there. Now, as far as making artificial gravity, the only way we know to make artificial gravity at this point is to put ourselves inside a rotating ring or, a big cylinder where we rotate the cylinder. And we rotate it enough so that if you're walking on the inside of the surface of that cylinder, going around and around and around, you're being pressed against the walls of that cylinder on your feet with the force of gravity of like the Earth. We call that 1G, 1 times the force of the gravity here. That's
Space Odyssey. Isn't that how?
It's 2001: A Space Odyssey. That's why Kubrick made sure that the space station was spinning, because through the windows you watch the Earth doing this weird little pirouette every few seconds as it goes around, because it's looking at the Earth and spinning in orbit. So that would generate one gravitational, increment at the distance out on the hub at the walls of that circular spinning spacecraft.
But
so,
that's really not gravity at all.
It's you want to call it centripetal acceleration or a centrifugal force. We can do that too. But it's actually it's not gravity. It's simulated gravity.
Artificial, yeah.
Yeah, we're talking about the artificial gravity, yeah. And Daryl's right. Okay, if you want to talk about gravity, you would need to somehow make the space station have as much mass as the Earth to be able to stand on it and jump up and just fall back down the same way we do on Earth. But the acceleration force, that force that sticks out there, that puts you out there, okay, that is how we have to simulate gravity if we go into space. That's the only way we can do it.
And Charles,
you talk about the 4 forces and gravity being the weakest of the 4. Well, as I understand it, just from a layman's perspective, the strong force and the weak force, they're the 2 strongest, but they're only really work over very small distances, like inside the nucleus.
That's correct.
Then you get the electromagnetic force, which is stronger than gravity, and it has long reach. But gravity, even though it's the weakest of all, it has the longest reach. If you had a universe with only 2 particles in it, they would eventually gravitate toward and combine.
Yep, that's true. But the way to look at that is look at the size of the atoms. Look at the size of the particles relative to the nuclei size. And when you look at how powerful the stored energy is within an atom, if you rip an atom apart, all right, especially if you're using like the strong force, okay, and like ripping neutrons away from protons in an atom that's bound like that, now you're talking about so much energy is being released because so much energy is stored in there. And so in terms of gravity, we don't see those kinds of energies at the gravitational level. We see them at the strong nuclear level. And we also know, for instance, that, atom bombs, right? I mean, atom bombs are fission bombs and fusion bombs. But the fission bomb, it's, I'm trying to remember the original design. It was like they had these projectors that would all target a coordinated explosive that goes in toward the center against the radioactive material. And that would cause a cascade of neutrons to be liberated from that core nucleus called the Demon Core, by the way. That's what they called that, the Demon Core. Because
I guess.
Right?
Yeah, that was the plutonium bomb in particular.
Oh.
Yeah. And the Demon Core killed a number of scientists, who were exposed to its, that cascade effect in like a split second. If they lift the cap and too much of the neutron cascade got out, they'd be hit with lethal dose of neutrons in no time. So, I mean, it's really bad news.
I saw an interesting video the other day on YouTube of the construction of the radioisotope power generator for the Perseverance rover. And it has the plutonium core.
Mm-hmm.
And they showed that core, and that sucker was so hot, it was actually sitting there glowing red.
Yeah. The thing about those radioisotope thermoelectric generators is their purpose is the power supply for like rovers and things, Curiosity especially, and now Perseverance, as you point out, Daryl, Cassini. Well, those probes and rovers, that RTG, as they're called, that power supply, only has a finite amount of power. It will run out eventually because it's that reaction, that decay going on, which will eventually run out. And when it runs out, then the power is going to drop. Now, the rover needs mobility through electricity, and it needs heat, to maintain any potential other units that require heat. Because the Martian cold is what kills things, right? And depletes batteries and things like that are additional. And it will kill electronic units as well. So they actually have to very carefully manage that heat. So this rover, I imagine even on Mars, parts of this rover are going to be probably too warm to touch, even as humans walking up to it. But none of that stuff gets out. Those RTGs are so powerful. They've dropped them from airplanes. They've actually, not with fuel in them, but they've dropped them to try and see if they could ever be broken. They've hit them with missiles. They've hit them with tank shells. They've run over them, and they can't get the RTG casings to shatter, break, or leak. So that's why they're considered so safe. So, for instance, if a probe accidentally crashed into our atmosphere, it wouldn't suffer just because if it hit the ground, it would cause suffering and leakage of radiation. I'm sorry, Amanda, go ahead.
No, I had a question from Charles, but finish your thought, please.
Okay, no, I was just saying that these RTGs are very well thought out, and of the nuclear power we use, I think they're probably the safest. They're better than a Fukushima nuclear reactor, for instance, where, and you've heard me talk about nuclear power before. I look at nuclear power as being in a deep valley. In order to get the reaction to stop, you got to push that out of the valley. You got to push that reaction out of the valley. And that's those rods that come down to quench the reaction, all right, because there are fuel pellets in these rods, all right? And you got to lower something down physically, mechanically, into a reactor to stop that from happening. But if there's electricity failure or if it gets too hot, those rods warp. And the channels for these rods, these inert rods that are supposed to stop the reaction, they might warp and you can't push it in. A submarine was lost that way by the Russians, okay? And then, so that process, that problem is why it's like a deep valley. You have this deep valley where the reaction's happening way down here. To get it to stop, you've got to do all kinds of mechanical work to get out of that valley. Fusion, on the other hand, if we can do that, fusion's like at the tippity top of a steep hill with a really tiny point. The reaction's very finely balanced on the top. The slightest out of balance, boop, it falls off and shuts down. So you see, that's why fusion is so much better. It's safer. You can't get a nuclear meltdown with fusion. If anything, it stops working and say, hey, Frank, you forgot to balance the reaction, and it shut off again. That's better than like Chernobyl, where we forgot that we hit a button that was supposed to scram our reactors and it blew up.
No, it didn't.
Yeah. Oh, that's right. No, it didn't. Shh. Okay. So anyway, Amanda, go ahead. You can ask now.
Yeah, not having a meltdown is always a huge selling point in my opinion.
Yeah, I think so.
Yeah, but before we got away from gravity too much, Charles asks an interesting question. Is gravity necessarily fixed to momentum and inertia?
Okay, well, that's a really good question, Charles. Now, if you think of it this way, momentum is the mass of an object times its velocity, right? So that gives us the momentum of an object. And that object will have mass. So clearly, there will be a component, a gravitational component that's built into some type of momentum study. Inertia is the how do we say, the ease at which you can move an object. Okay, if it's a 200-pound mass, it's a cube sitting on the ground, you're going to have to push really hard. But if it's a round ball, you can probably roll it on a nice flat surface, right? So the ball's easier to move. Its inertia is going to be less. Its moment, it's called moment of inertia, will be less than that of a big cube of steel sitting on the ground that weighs 200 pounds. Okay, so that said, because there's still mass involved, yes, gravity is going to play a role. Out in space, though, in the absence of anything else, all right, so we're not on Earth anymore, then gravity won't play a role. All it plays a role is the inertia, the ease at which you can move it in space. But if you push on something in space that's your weight, the two of you are going to go equally apart from each other. Okay? I should say your mass. And if the two of you, if you weigh twice as much as something you're trying to push here on Earth, okay, you push it and it'll more easily go. In space, if your mass is twice as much as the object you're trying to push, okay, then you'll get it to move, but you're going to also move backwards slightly as well. You're going to move backwards slow, and this will move back. This will move out. The other one will move outward faster. Right? Sort of like like a croquet ball. You know, you hit it and you transfer force through a ball to knock a ball farther away. Well, those collisions will occur, and when you push something out in space, it's going to have to do more with the ease at which you can move it, and that relates to the moment of inertia as well, of course, as its mass. All right, but on Earth, gravity plays a role. All right. So I think that makes sense. Any others, Amanda?
I hope that does make sense. Not at the moment. I'm sure Tara has some built up, though.
I know she does. I would like to hear more.
I'm kind of going back to this temperature thing real quick. You said that, I mean, that the temperature, the warmth, but isn't cold a temperature? Isn't it cold in space? And can't you measure that? Because you said there's really no temperature. Are you talking just about warmth? But there's cold.
Okay, yes. Now I know what you're getting at here. Temperature is a characteristic of a substance that you can measure. And that is based on however it was heated up, okay, whether by radiation or whatever, right? So, and cold is, of course, a temperature. You can have cold temperatures, of course. However, if you put a thermometer out in open space, you're not going to get a reading as long as it's not facing the sun or whatever. And the reason is because there's no medium through which the temperature can be conducted, okay? Soil on the moon can conduct temperature. If you stick a thermometer down in the soil of the moon is absorbing radiation, okay? That radiation gets converted most likely to heat, and the temperature on the thermometer will change somewhat. The moon is a very cold place anyway, right? But on the surface in the sun, the temperatures can be hundreds of degrees above zero. In the shadows, they could be hundreds of degrees below zero, you know? But the thing is, if the soil conducts heat, if you have two particles next to each other, this one gets hot, this one's going to get hot too, because they're touching each other. And that'll go for some distance through the lunar surface. So if you have a crater, like this, for instance, okay, and you have something hot at this side of the crater, then it's possible that the heat will transfer through the soils to some distance, maybe to the other side of the crater, maybe not quite. But if you measured it, you'd see like a little round area where the heat had been distributed before it trailed off to nothing again. And again, it's being conducted through the soil by the particles that mutually heat each other up. But then that tapers off over time. All right. And so that means that even though there's no air on the moon, we can still measure temperature as long as we have a medium through which we can measure it. And that medium in this case would be the soil.
Yeah, and this gets into the idea of what a vacuum is. I mean, a vacuum is literally nothing. A hard vacuum out in space, there is no perfect vacuum, but when you're out in open space, you may be talking like one molecule per a cubic meter of space, of volume. And, well, that one little molecule may be hot, but out in the totality of that volume of space you're measuring, I mean, it becomes meaningless because it's mostly just nothing.
That's right. And it really is the medium through which you can measure temperature. Think of it this way. The bulb on a thermometer, you touch it with your thumb, it'll go up. Well, if you touch it with your thumb in space, it will go up. Take your thumb off of it, however, and it'll go down. All right? Because it's radiating whatever heat your thumb transferred to it, it's radiating that heat away. And so the temperature reading will go down until it reaches an equilibrium temperature that's the same as that relates to like the amount of heat lost by radiating away all that heat. Okay? So when all that heat is radiated away, that's the temperature. The reading on there will be the temperature. That's not the temperature of space. Okay? That's the temperature loss. Okay? That's the temperature loss from your thumb being against the bulb of the thermometer. Right? You're heating up the bulb of the thermometer right here. Take it away. Now that heat radiates away. Okay? So it gets down, 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 down. And then when all that heat is radiated away, nothing else happens. It won't go up. It won't go down.
You want a little household hint? They used to advertise a product on TV late at night. It was like the Magic Trivet or something.
Yeah.
You'd take this thing, you'd set an ice cold, piece of meat from the freezer on it, and it would magically warm up faster than if you didn't do anything. Yeah, well, you can do the same thing. I do this. Say I was going to make some chili for dinner, and I got a pound of ground beef to defrost. I take my cheapest aluminum pan, I set it on the stove, I set it on the counter, wherever, and then I just set that package on top of that cheap aluminum pan. Now, let it sit for a while, go feel that pan, and it's going to feel ice cold. It's not that the cold is moving from the package to the pan, it's that the heat is being drawn into the package from the pan. In the case of aluminum, because it conducts heat so well, it is still warmer than the package of frozen meat, to put it that way. I've done this. You can check it both ways. Put one on the pan and leave one out, and the package you set on that aluminum pan is going to defrost a whole lot faster than if you just set it on the counter.
And if you put it on a thick aluminum plate, it might actually happen at a higher rate.
Absolutely.
Because there's a lot more density of aluminum there.
Yep. So,
and that's a really cool thing. And I actually encourage everybody to try Daryl's idea. Go into your freezer today or tonight and just pull out some meat and stick it on an aluminum pan, and then just walk away and then come back. Now, if the dog hasn't eaten it or gotten at it, or the cats didn't run away with it, then you'll find that that's true.
And Cooking with Daryl will be coming soon to KGRA, so look forward to that.
Yum.
Tara,
I think you got our listeners' stomachs growling, and Alan's coming up next, so try to grab a snack in between shows if you can to make it through the night.
That's right. Now we only have time for probably one more question, Tara. So,
well, just real quick about are all these astronauts that are going into space, are they being trained in astronomy? Are they astronomers as well? Do they need to know about the heavens to be up there?
No. They don't actually, but some do anyway. Okay, because that's what sparked their interest in the human space program. But
back in the days, they taught them celestial navigation, just like they did in the Air Force. To find your way around.
That's right. They had to, because they had to have a backup for times like. But today, no. There are people that go up there that are PhDs in chemistry who don't even know what's up in the sky. Okay. And that brings me to another point too. And we only have a couple minutes. I get it. But if we talk about, for instance, airline pilots, people say they're the best observers. They know everything in the sky that's astronomical or not. You know what? That's absolutely false. I know that for a fact. Okay. There's a lot of airline pilots that have no clue what's in the sky, but you know what? They certainly know if that thing over there is an aircraft coming at them. And they know if that is an aircraft above or below them. They have an idea of how far away that is. And I think that all this stuff is why, okay, we have to keep in mind that everyone has their own expertise and specialty, okay? And when we talk about people that are astronauts, well, most of them were pilots, and most of them were Air Force originally. And as Daryl says, many of them had to be trained in celestial navigation, but because they actually had to use it in some cases to navigate the earlier capsules, and that type of thing was really, that's scary to me, because, imagine being in weightless 0G using a slide rule, that's some of what they did, or these little planisphere calculators. Daryl knows about those. I think he's talked about them in the past.
We have probably talked about them in the past, and I'm sure we'll talk about them in the future. But since I'm piping in, you know what time that is.
I know. I'm actually there. I'm ready to go.
I'm on it.
Yeah, I'm on it. It only took me 3 breaks?
3 years.
Yeah.
Well, first you don't succeed.
Hey guys, you know what? Thank you for joining us tonight on SkyTour Livestream. I hope you SkyTour Radio rather. A little update, SkyTour Livestream is coming along on the 28th of March. I'll be out in Arizona. We'll be setting it up and going full tilt. All right. More on that next week. But for now, I want to thank Tara so much. Thank you, dear. I want to thank Daryl, of course, and Amanda. And you guys have been amazing out in the audience. The questions are unparalleled and excellent. So thank you, guys. And we will talk to you next week. And remember, when you go out, keep looking up.
Except while you're driving.
Good night, everybody.